In the previous episode, we talked about the first ingredient in the particle discovery recipe, which is the fact that you have to start by producing or creating the particle that you're searching for. Today, we'll explore what happens next. So how can we detect the Higgs boson? We have these beautiful particle detectors that can detect electrons, muons, photons, other particles, but can they detect Higgs bosons? Well, no, they cannot. That's because the Higgs boson doesn't exist for long enough. It has a lifetime of about 10 to the minus 22 seconds. So pretty much the moment it gets produced, it immediately decays into other particles. It never gets a chance to reach any part of this detector. So we cannot detect it. How do we know it was there? Well, that depends on what it decayed into. There's a few possibilities. We call that different decay modes. It can decay into different particles. But here we're interested in the decay into two photons. Now, side remark, the Higgs cannot directly decay into two photons. The process is a bit more involved. But for the purpose of this video, the details don't matter. What matters is that there's a Higgs boson at the beginning and two photons at the end. So these two photons are what our particle detectors are going to see and measure. The problem is that we see photons in our detectors all the time. There's many ways you can produce photons in particle collisions. So just seeing two photons at the same time is not a sign that you have just produced a Higgs boson. But that information is encoded into these photons. How? Well, to understand that, let's look in more detail at what happens in the Higgs decay. So let's say we have just produced the Higgs boson and it's sitting right here in the center of our particle detector. If it's not moving, the total energy in the system is just the mass of the Higgs times c squared, of course. Now, what happens when it decays? You suddenly have two photons traveling in opposite directions. The total energy in the system now is the sum of the masses and the kinetic energies of the two particles. But since the mass of the photon is zero, this and this are not there. And we're left with just the two energies of the two photons. Now these have to be equal due to momentum conservation. And since the total energy in the system hasn't changed, both photons will have the same energy, equal to half the mass of the Higgs. So in this process, the mass of the Higgs turned into the energies of the two photons. Our particle detectors will detect these photons and measure their energies. So if we see two photons going in opposite directions, both having energies equal to half the mass of the Higgs, is this the way that we know the Higgs was there? Well, it could be, but the bad news is that this only works if the Higgs was produced at rest, with zero momentum, which basically never happens. In the collision, the Higgs always will get some momentum. So then, the photons will no longer go in opposite directions, and they'll have different energies. So just adding the energies together will make no sense. The good news is that it doesn't really matter, because even in such a situation, you can still access the mass of the Higgs, only in a different way. How? Well, forget for a moment that the Higgs has such a short lifetime, and think of it like this. If the Higgs has momentum, it means that it's moving. If it's moving, you can imagine walking along with it. Now, how would that situation look like? For an observer walking along with the Higgs is not moving. So we're back to the simple situation from the beginning. The photons go in opposite directions, you can add their energies and get the mass of the Higgs. But in our particle detector, which is of course standing still, you can measure the energies and the directions of the photons. And from these measurements, you can calculate the movement, the motion of the Higgs, the momentum of the Higgs. And from that, you get the center of mass reference frame, which we saw just a moment ago. So you can calculate the energies of the photons in that reference frame, and voila, you add them together, you get the mass of the Higgs. Now in practice, the way we do this is slightly different. We make use of the fact that energy equals mc squared, but this is only for particles that don't move. To get the general form of this equation, you have to add the momentum and square everything. Now, from this, you can extract the mass. the mass is the energy minus the momentum and square root. Now this is what we call the invariant mass of the system. If the system is just one particle, then this is the mass of that particle. But if that particle decayed into several particles, the invariant mass of the system is still the mass of that parent particle. And you can calculate it as the sum of the energies of the particles and sum of their momentum vectors. So in our example, a Higgs boson decayed into 2 photons. And if we're in the center of mass frame, the photon momenta add to 0, and the invariant mass is the sum of the energies of the 2 photons. But if we're in a different reference frame, we just need to calculate this, and we'll get that mass. So the bottom line of all of this is, when we detect 2 photons, we can calculate the invariant mass of the 2-photon system. And if the 2 photons come from the decay of the Higgs boson, this mass will be the mass of the Higgs. Okay, so it looks like we're almost done here. We just need to go through the collisions, find the ones that have 2 photons in them, calculate the invariant masses of these photon pairs, and when we find a pair where that mass is the mass of the Higgs, bingo, we have a discovery, right? Well, unfortunately, it's not that simple, for 2 reasons. First of all, before we found the Higgs, we didn't even know its mass. So we couldn't look for pairs of photons with the mass of the Higgs because we didn't know the mass of the Higgs. And second, as we already said earlier, there's many photons produced in the particle collisions. And that complicates things quite a bit. So we're going to need one more episode. Episode 3, called Analyze, in which we will deal with all of that.